All right, so this is Carnegie Mellon 21499 Lecture 2. This is going to be talking about sum problems in more sum than difference theory. So what's interesting is this and the previous talk are essentially the only two times in my life where my research trajectory changed after hearing a talk. Both of these subjects, my interest was inspired by a talk I heard. So for this one, the talk was by Mel Nathanson at Brown. And I just became very intrigued with these objects. And so I want to talk to you a little bit about why you might look at problems like this, what are the issues you might study, and what I would love people to do. So we started looking at one of these things 3 years ago here at Carnegie Mellon, and we made some progress. Then we broke through some barriers this past summer at Williams and have made tremendous progress. I will be careful because this is being recorded. We have had simulations running at Williams which we need to extend our results. They have been running since essentially the start of the fall semester. They're now maybe around 80% done. They will finish before the spring is over. I know there are some people here who have very strong programming skills. You might find a way to make the code even better, which would allow us to get even stronger results. And for the real problem I want to do, the level of difficulty is the square of what we've been doing. And so computational expertise will be essential for this. All right, so I'm going to introduce you what more sum than difference sets are. I'll talk a little bit about the dividend one, and then probably talk a little bit about some future research. All right, so let's say A is a finite set of integers. We're going to overload notation, and absolute value of A is going to be its size. So the sum set is the set of all possible sums, and the difference set is the set of all possible differences. So this is an interactive talk. Which do you think is larger? In general, the set of sums or the set of differences, and why? And as a hint, either answer can be justified.
Differences, because differences are not commutative.
Good. Differences are not commutative. So 3 minus 4 and 4 minus 3 are two different differences, whereas 3 plus 4 and 4 plus 3 are the same sum. So this is one reason why there should be more differences. Can somebody give me a reason why there might be more sums? What's 3 plus 3?
Wait, is it being recorded?
Yes.
Oh. I was going to say they declined the card because I had the wrong zip code, so I'm just going to go down there and grab it.
No, I'll give you the zip code.
Why are you? It got too complicated. Like I think I'm.
All right, just take this and use this when you go there.
Well,
just make the reimbursement better.
Okay. What was the zip
All
code?
right. Give me a piece of paper, somebody. Oh, here. Yeah. Does somebody have a pen handy? I got one. All right. Here you go.
Is there anything else I should know?
That should be it. All right.
All right. I'll be back as soon as I can.
Yep.
I'm going to leave my bag here.
Okay. So 3 plus 3 is 6. 3 minus 3 is 0. 4 plus 4 is 8. 4 minus 4 is 0. When you look at the diagonal, when I equals j, that's going to give you a lot more sums, and they're going to keep giving you the difference 0, 0, 0, 0. But if you have a set with n elements, you have basically n choose 2 ways to choose distinct indices and only n ways to choose the same index. So as the number of elements grows, the diagonal component is going to be very small. So you expect that the contribution from the diagonal is not going to be enough to overwhelm this. So in completely obvious notation, we say a set is sum dominant if there's more sums than differences. It's balanced if they have the same, it's difference dominated otherwise. And it's natural to think that there's more differences typically than sums, and we've explained why. It does happen, though, that you can find sets that have more sums than differences. So this is the smallest one, and there's a lot of research about how do you find which ones can be the smallest, how many ones can you find of a given size, where can they be. And then Martin and O'Brien, this is the Blitzkrieg proof, shocked the community when they proved back in 2006 that if you choose each element independent from all the others to be in your set with probability of half. So this is the uniform model. Another way of looking at this is all possible subsets are assigned the same chance of being chosen. If you do that, then the proportion of more sum than difference sets is bounded below by a positive constant that's at least basically 10 to the negative 7. We now believe it's around 10 to the negative, I think 4, 4.5, something like that. When you looked at the numerics, it looked like in the limit, it would be 0%, there would be some dominant. But it's actually positive percent. And if instead of choosing the sets to be drawn uniformly, if you choose each element with a fixed probability p, you will still have a positive percent of some dominant sets. So this was a very surprising result. That's what I want to say. I'll say just a little bit more about this. Some work I did with Peter Hegarty, we looked at other models where instead of choosing each element with a fixed probability p, we allowed the probability to decrease with n. And depending on how rapidly it decreased, you could get a lot of interesting results about the probabilities of being some dominant. And as long as it decreased at any rate, in the limit it was 0% some dominant. And there was a transition behavior when the probability of choosing an element was like 1 over square root of n. So if you remember from your physics or your chemistry, the phase plots, the solid, liquid, gas, and you have these nice curves in the plane, and as you cross the curve, you have a transition from, say, liquid to gas. You have transitions like that in problems like this. And whenever you have a phase transition, something interesting is happening. And so there is a phase transition there. It turns out a typical set is missing, I think, 7 differences, and a typical set is missing 11 sums. Okay. But maybe there's some kind of correlations or whatnot. This is what's happening for the average. But maybe there's a couple of sets that just have a lot fewer sums that are missing, and a few that have a lot more differences. And so maybe it is possible for there to be some dominant sets. So this led to the question of, well, what can you say about the distribution of sums? Well, if you take the uniform model where each element happens with probability a half, if you have n possible numbers, about how many of them should you choose? N over 2. And what should the fluctuations be like? What size? So this is basic probability, or central limit theorem. So if you haven't taken a probability, that's fine. It shows that the fluctuations are like square root of n. So the standard deviation in this model is going to be square root of n. So if n is very large, like 10 to the 100, you would expect the number of elements to be chosen to be like 1/2 10 to the 100, and you would expect the fluctuations to be of size roughly plus or minus 10 to the 50. Let's put this in perspective. If I were to give you $1,000 tonight, would you be happy? If I tell you, oh, I made a mistake, I meant to give you $10 less. I meant to give you $10. Would you be happy? Yeah, but not nearly as happy as when you were getting $1,000. The error of plus or minus, 990 is huge when your number's of size 100. If I tell you I'm going to give you $1 billion, and say, oh, I made a mistake, I meant to give you $990 less than $1 billion, is there any noticeable change in your happiness? Okay. If there was, you would have a much finer appreciation for the value of money than most people I have met. This is well within the level of noise. So when you ask a question, how big is something? It's always going to be, well, big relative to what? I work on, the school budgets. We have a $21 million budget for the district. We get $3.5 million from the state in Chapter 70 funds that we have to allocate between the 3 buildings. Is $3.5 million a lot of money? Yes, and it's actually not a bad percentage of 21. If you said it was a $20 million budget, you'd multiply by 5, and so you're already over 16%. That's a significant amount. But it's always, always relative. I will just skirt politics. I will not get into discussion of merits. Is $5 billion or $5.7 billion, is that a lot of money? A lot of it is relative to what? What is the U.S. gross domestic product? What is the U.S. fiscal budget for each year? How much of a percentage of that budget is $5.7 billion? Whenever you have a number, you want to put in perspective. Since the fluctuations are of size square root of n, if the fluctuations are of size 10 to the 50, and we said, all right, the number of elements we expect to be in our set is roughly 1/2 10 to the 100, plus or minus is a couple of multiples of 10 to the 50. You can't notice the multiples of 10 to the 50. This is like Bill Gates' accountant telling him, we were off, you have $1,000 less than I told you. It's not worth Bill Gates' time to process that information. Okay? So when you look at these models, instead of counting the distribution of sums, almost every sum is realized because most of these sets have roughly n over 2 elements. And when you look at ways of adding numbers to each other, there are so many ways to get numbers that almost every number is realized. And this is why I said you're typically missing only on the order of like 11 elements or something like that. Most things that could be realized are realized. So rather than looking at how many sums you have, it's more natural to look at how many sums you don't have. And so we look at a plot of missing sums. And this is from the uniform model. And if you look at this, you should notice that there is something interesting. It's going up, drops, goes up, and drops again. If you have taken any good probability stats class, you will essentially see unimodal distributions. They go up, they go down. This is what up, it's more like a roller coaster. Now, this little part over here is probably the mildest possible bump you can have, where we had to do a lot of work to prove that there was a drop there. But there is a drop. So what kind of questions does this lead you to ask? So you want to try to create new research questions. So we did enough computation, so it's a mixture of theory and experiment, to prove that that is lower than the stuff on the left and the right. What questions would you like to ask?
Why is the drop there?
So one is, why is the drop there? And again, we've proven it, but the proof is not the same as explaining why it's there. What's another question you could ask?
Is it only the uniform model?
So what would happen if you used a different probability? And so I'm going to switch. Oh, okay. Okay, so this is the right one. Okay, I can just do this one. Yeah. So here's a plot of what's going on with different probabilities. So anybody ever read XKCD? XKCD is a wonderful comic strip. And if you hold your cursor over the strip, it gives you additional jokes. So one of my favorite strips is a girl goes up to her boyfriend and says, I think we should break up. And he looks at her and she goes, here's my analysis. And he looks at it and he goes, I agree with you. And she goes, I thought the statistics would be convincing. Oh, no. You didn't label your axes. I can do better than someone who doesn't label their axes. This is one of the most common things that people forget to do. Label. So over here you want, well, what is Q? So there should be something that tells you explicitly what is everything. If you are generating things, if you're using LaTeX, save the code in your text file. Just comment it out. And then that way, if you need to fix things, if the journal or somebody else wants you to modify things, if they want to change a little bit of the data you have the stuff there. If it's simple. If it's more complicated, then you have it in a separate file. So here, Q is the probability of not choosing an element. So the smaller Q is, the more likely we are to choose. Is there any value of Q where you know exactly what the answer will be? So Q is the probability of not choosing an element to be in your set. And each element from 1 to n is chosen uniformly, it's chosen independently with probability P, which is 1 minus Q. What Q do you understand immediately?
Q is 0, we choose every element.
Yes, if Q is 0, we choose every element. And how many missing sums do we have?
0.
0. Are there any other Qs you understand? 1. You choose no elements. Okay? So in those two cases, we understand everything. As an aside, if you do information theory, let's say you want to send messages from person to person, so you have to use bits, and use zeros and ones, and you want to transmit the bits correctly. What is the best probability for transmitting a bit? Success rate. 100%. Because if you always transmit correctly, if the recipient receives a 1, they know you meant a 1. If they receive a 0, they know you meant a 0. What's the worst success rate? 1/2. It's not 0. If your success rate was 0, what would the recipient do? They would just flip it. So actually the worst success rate in information theory is 1/2. And if you look at a lot of the results in the subject, when the probability is 1/2, that's when you have the worst results. Are there any Seinfeld fans here? There's a character in the TV show Seinfeld named George Costanza. I don't think anybody would dispute the allegation that he's a loser. His life just always goes wrong. And there's one episode called The Opposite where he's remarking to his friends that every decision he's made in his life is wrong. So his friends advise him, well, you should do the opposite. And so he starts doing the opposite, and there's some very funny scenes where he goes up to an attractive woman and says, my name is George, I'm unemployed, I live with my parents. Hi, it's so nice to meet you. And then she ends up getting him an interview with the New York Yankees. The owner of the New York Yankees walks in and says, it's nice to meet you. And he goes, well, I wish I could say that to you. And then starts unloading about all the things that he believes the owner of the Yankees has done wrong. Typically in life, do you have more than 2 options? Yes. So sadly in life, the strategy of doing the opposite is typically not going to work. But it is interesting to see connections between what we're discussing here and other parts of mathematics, which is something I want to highlight. And just what is actually best. And sometimes it's not what you would think. A 0% success rate could actually be very good for a lot of these problems. So what we can do is we can look at what happens to the location of the divot. And so here is our divot at 1/2. And then you can see the divots seem to be in other places as we change the probabilities. So you can generate a whole slew of questions. What kind of questions might you want to generate? So a lot of people have expressed interest. Give me some questions.
Can you describe the position of the div with respect to the probability?
Yes. And so for instance, if I have a divot here with the probability at 1/2, is there an open interval is there an interval that contains 1/2 where there will always be a divot there? And I believe we can prove something like that. That you have some kind of continuity. That if you have a divot, the divot will still be there if you change the probability by a small amount in one of the directions. Or probably in both directions because there's a finite amount that it's dropping down. You could also ask, do you have more than one divot? Is it ever possible to have more than one divot? When you start looking at these, if you look at q equals 0.6, what do you think looks interesting? Looks like there might not be a divot at 0.6. So maybe is there some critical threshold beyond which there is no divot? We proved that there exists a divot at 6 or 7. We didn't prove that there can't be a divot later on. These probabilities are all so small, it's really hard to analyze. So the way this project would work is to try to calculate what is the probability of observing a fixed number of missing sums. And then I would love to generalize this work to trying to understand the distribution of missing differences. No one's really done this for the difference set because the difference set is much harder. All right, so let me see if I can. Trying to tell it to move the screen up. All right, does not want to move the screen up. plan B, right? Always have a plan B. So let's say you have a set, so we have a set of numbers. And what I'm going to do is I'm going to break the set into different regions. So what we're going to have here, this will be the left part, this will be the middle part, and this will be the right part. So most of your set is going to be the big middle. Okay? And what you can do is you can look at what is A plus A. So I'm going to write A is equal to left, union, middle, union, right. And I'll say that that's just left, union, middle, union, right. And then A plus A, how can I get things in A plus A? What could I have? So I've split A up into three parts, the left part, the middle part, and the right part. How could I get something in A plus A?
I mean, like left plus left.
I can have left plus left.
Union, left plus middle, plus right.
So we've got to figure out what order we want to do things. Okay, and after left plus middle, what do you want to do after that?
Left plus right.
Okay, anything else?
And middle plus middle.
No plus middle.
And middle plus right. And right plus right.
Okay. So when you look at A plus A, the stuff on the far left of A plus A is going to be from left plus left. And the stuff on the far right of A plus A is going to be from the right plus right. And then what's really going to go on is, if you're at least in a uniform model, you're going to have so many elements in the middle that essentially all this stuff in here, you essentially get almost all of it. And maybe with even a high probability, you get all of it. And then the missing sums is going to come from left plus left and right plus right. And so you want to understand really just what's going on there. And then you do some what's called abstract nonsense to handle the stuff in the middle. This is following work of like Martin and O'Brien, who proved that great result from 2006. So how do you handle left plus left? Well, what you can do is you can actually just enumerate all the possible left fringes of a given length and look at what happens when you add left plus left. The distribution of right plus right is actually going to be symmetric. So what you can do is you can say, let's say we assume left and right are drawn from a set of size m, of size x. X is independent of n. So I'm going to fix the length for my left and my right. So it's not going to be growing. Or maybe I'll let it grow very, very slowly, but probably I'll keep it fixed. And then I look at all possible lefts. And essentially, if I just shift them all down by the same amount, that gives me all possible rights. So if I look at the distribution of how many things I'm missing in left plus left, I'm essentially getting the same stuff for right plus right. And then what I would do is I would basically multiply how many are missing here by how many are missing there. If you do different sets, it becomes a little bit more complicated. So I've started to work on this with some of my students from last summer. And so we have some partial results on pushing things forward. And so I can share working notes on that. And we've got some results when the probability of choosing an element is high, from 100% down to maybe around 70%. We have a good idea of what's going on. And we'd love to push that further. And a lot of that is going to have to be taking larger sets here. And we would love to try to apply this to the difference set. Now, I know some people have taken linear algebra. So this becomes a very interesting question of, it's not enough to be able to theoretically prove that you have a path that will work. You need to be able to have something that you can implement if you're using the computer. And there are certain things where the universe, let's say every subatomic particle in the universe was a universe. With every subatomic particle in those universes, a supercomputer devoted exclusively to you. And each one of these supercomputers is running since the dawn of time. And that would still not be enough to factor some of the numbers that are being used in modern encryption. Just to get some level of the difficulty. Just because it's a finite calculation doesn't mean it's a calculation we can do in a reasonable amount of time. So for problems like this, we have to be really clever as to how do we approach it. So for the left plus left and the right plus right, that's basically the same distribution. If we now did the extremes, we can basically be having the same set in each one. We have to worry a little bit about some overlap. Well, maybe left plus middle could overlap with left plus left. But if it overlaps, it can't overlap in the very beginning of left plus left. The extreme beginning of left plus left is going to be well before the middle kicks in, even if you take the 0 element. So there's a lot of bookkeeping you need to do. And what you want to do is you want to do this for all probabilities simultaneously. You don't want to have a long calculation and then have to run it for every choice of probability from 0 to 1. So what you do is you look at each set. And so what you can do is say L equals L1, L2, dot, 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 LK, which is a subset of 0, 1, dot, dot, dot. Okay. I'll do it with 0, 9 just to make things a little bit nicer. Okay. So we choose a subset of size K. What's the probability we chose that subset? It would be 1 over 2 to the x if every element was chosen with the same probability. So if the probability is 1/2, if p equals 1/2, then the probability we chose L will just be 1 over 2 to the x. What will the probability be in general? So what we can do is every time we choose k elements, we can just increment basically like a polynomial counter by 1. And then for that we'll know how many we'll know what the missing difference is that it generated, or the missing number of sums it generated. And then we keep track. And then at the end of the day, we then evaluate it for various values of p. And this way we can do all the p's simultaneously in terms of just how we're storing the stuff. So yeah, if you go into this problem, I'm happy to talk in greater detail about stuff like this. But I just wanted to give you a sense that there is a way to attack these all at once. All we care about is how many missing sums does it have and what did it add. So what we can do is we have various polynomials. Maybe the polynomials are P1, P2 of P dot dot dot, and if missing exactly K sums, we increment the missing by K by the polynomial Pk of P. And we do something like this to just keep track of how many times when we're missing by K sums, it's coming from this polynomial. And so I may have written things slightly wrong, but there's a way to just do the bookkeeping. Now, it's going to be much harder for the difference set. So if we have the difference set, what will we need? So what would we need for the difference set? So A is still going to be left union middle union right. We want to study A minus A. So what would A minus A be?
There will be 9 choices.
Okay.
L minus L.
We have L minus L.
L minus L.
What
L
else?
minus M.
L minus M.
And so on.
And then we'll have
L minus L.
L minus L. Then we'll have M minus M union M minus left plus your times your order M minus R union R minus R union R minus M union R minus L. So what's going to give us the extreme fringes?
L minus R and R minus M.
Okay, so L minus R. I hope that's going to be visible. Now notice that this is different. Is there a relationship between L minus R and R minus L? Yes. If we understand L minus R, we understand R minus L. We can multiply through by -1. That's not a big deal. But notice that for each of these, we have to deal with 2 different sets. An R is chosen and an L is chosen. Whereas here, I don't think I can go through this anymore. Where over here, the L plus L, we've just chosen one set. And the R plus R, it's one set, and it's the same by symmetry as what we're doing over here. So we only have to be choosing one fringe. Here we have to be choosing 2 fringes. And so when you look at the complexity of the calculation, it's going to be much, much worse. So it's going to be a real issue to try to figure out how to do this problem in a way that will give us a reasonable answer in a reasonable amount of time. It is a mix of theory and experiment and computation. And again, if you're interested, I'm happy to share the notes on this. Okay, any other questions on this part? All right, do you want to hit stop?